What's up, everyone? I am back with another, you guessed it, repair video. It's Sunday. It's a beautiful day in Philly, like mid 70s. Really nice. And yeah, we got this box here. So, what could be inside here? Another piece of test equipment? No, actually. So, this is actually for my partner. I guess it's kind of for both of us, but it was really, we got it for her. But let's just open this thing up. Okay, oh, we got some bubble wrap. Nicely packaged, don't give them credit for that. Another box. Is this? No. All right. It is a PlayStation 5. Okay. Yeah. So, my partner, she likes to play video games. I used to. I don't play them as often. Actually, I don't play them really at all. But she had expressed some interest in wanting a PS5. We don't have a gaming console right now. And so they're expensive. I think they're like $400, $500 new. And so I thought, what if we got one in non-working condition for much cheaper and fixed it up, and then you can have one? And she said, yeah. And that's what we did. So this is not working. Thought it'd be cool to do a video on it. So yeah, I've never repaired a PS5 before. I was looking specifically for one that wasn't powering on at all, because in general, if it's not powering on at all, that usually could be an indication that it's a power supply issue, which also in general, again, this isn't always true. The power supply is usually easier to repair, at least in my experience. So I was looking for one that wouldn't power on at all, and this one is, well, I haven't tried it yet, but we'll see. The seller said it doesn't turn it on at all. I did do a little bit of research on some of the electrical failures of these, and there seems to be many. And for example, the symptoms they give, like you hear of the single beep of death, or double beep, or triple beep, and they all mean different things, or could mean different things. And I asked the seller specifically, does it try to turn on? Does it beep? Does an LED illuminate? And they said no. So, yeah. I mean, there are people who, they're on YouTube, who their channel is dedicated to just repairing stuff like this. So I didn't want to look up too much about it, because I didn't want to just follow what somebody else did. I kind of wanted it to be fun. So yeah, I'm kind of going in here a little bit blind, except for that little bit of research I did, just so I didn't want to just buy a big paperweight. I wanted to, hopefully it be something that could still be fixed, and so that we could use it. But yeah. But anyway, it looks in okay condition. I mean, I got some scratches on the side here. But overall, it seems to be pretty good. That was another thing I did ask the seller. I was like, look, I'm not trying to buy something that was in a flood, or somebody opened up and took a circuit board out of, and they also said no. They do have returns, so you know, if I find anything like that, I will just have to return it. So yeah, but let's start taking it apart. Get started. Actually, before I do that, try to power it on. Well, the seller's claim is accurate. It does not power on at all, which is good. No LEDs, no beeping, nothing. So, and I did have a power cord that would fit it. So, let's take it apart. Alright, so I got the white covering off. So I'm just going to start removing screws. So that's the hard drive, disk drive. This had to come off first. And there goes the cooling fan. Alright. Okay, I'm going to reconnect this guy. So we don't get anything, but that doesn't necessarily mean that it's the supply. I think the best test would be to reconnect everything, including the power button, all these other connections I disconnected, and see if it comes on. So this is on the inside casing of the power supply. But I am not seeing anything on the unit that looks blown. But that looks like a burn mark. So, yeah. Alright, so found out a couple things. This is the power supply, the backside of the power supply board. I showed you guys that burn mark on the case of the power supply. And that part of the case would be on the underside of the board, alright? Now look at this. Hold on. Look at that. Can you see that? Let me do that again. Look at that. The joints are completely dry. And that's on this big resistor here. Okay. Completely dry. Look at that. Alright. So that's the power supply. There's a good chance this isn't working. I wasn't able to get it to power on. That's not all though. There is a short on the motherboard. And I can show you guys that now. So this is where the supply connects, and yeah. So got a short on the 12 volt rail. Now it seems like this is isolated to the 12 volt rail, which is good. Could be good, because if we check some caps that are definitely on a lower voltage rail, like for example this guy here, which is 6.3 volts, that means it must be at least, you know, it could be on a 3.3 volt rail or a 5 volt rail. But let's just check this guy. Okay, so there's no short across that guy, so that's good. But these caps here with that little compound on it, thermal compound, these must be on the 12 volt rail, because they are testing short. This is going to be a little bit difficult to find the short, alright? There's a couple ways you can do that. You could apply voltage and allow the you know, the current, you know, limit the current somewhat, but you know, allow it to get up some, you know, to a reasonable level, and then use a thermal camera and see what's heating up. You could also use a really sensitive meter that can, you know, measure in milliohms and see if, check for points on the board. If the resistance gets lower, that means you could potentially be closer to the short. If it gets higher, you're moving away from it. Unfortunately, I don't really have the ability to do either of those methods here at home. Alright, so a little change of scenery back in the lab. I brought it in here to work on it. it can just be difficult to work on things at home. And plus, I don't have a hot air station at home, which was definitely required to do some work on this board. There are some really thick power traces and ground traces on this board, so couldn't just work on it at home if I wanted to remove any components. But check this out. We found the short. The 12-volt rail is no longer short. This dual N-channel MOSFET. So there was a short between the gate, one of the gates, and the drain on that MOSFET. It is this component right here. This dual N-channel OptiMOS MOSFET. And yes, like I said, between pins 1 and 2, there is a short. And so this guy must be the culprit. So I'm going to order a replacement. I don't have anything like this in stock. I'm going to replace it, and I'm hoping that should get this guy back up and running. But, you know, it's really difficult to troubleshoot a board like this, especially without a schematic. So, you know, I'm hoping that MOSFET took the brunt. There again, it doesn't appear to be a short on the lower voltage rails, which is good. So hopefully the fault is only on the 12-volt rail. That would be ideal. All right, so we're gonna have to pause until that comes in. But what I can do is troubleshoot this power supply a bit further while I wait for that component to come in. Alright, so I resoldered in that resistor, and then powered it on. Still have nothing on the secondary side. Figured I'd just connect a load to it, see if it would come on. Still nothing. So there's definitely something still wrong with this guy. So yeah, we need to dig into this a little bit further. Well, I didn't have to look far for this one, because it looks like we got some shorted MOSFETs. I mean, they're short drain to source, gate, everywhere. They're in very close proximity to that resistor that was all burnt up. Wow, so I actually have something very similar. In fact, they're basically the same exact, you know, in the same class. The ones in there are the STF18N60M2. These that I have here are the STF24N60M2. So 600 volts, like those, but can handle 18 amps. And their on resistance is supposed to be even less. So I think it's safe to say that these need to go. These are dead. And I'm gonna pop these in and see what happens. Alright, we got our new MOSFETs in, and these guys are definitely dead. They test out of circuit short as well. Alright, let's power it on and see what happens. Alright, I figured I'd turn it on with the camera on just in case there are any fireworks, so I'm going to turn on my isolation transformer. Alright, and well, it doesn't look like we have any. We still don't have any 12 volts. We turn the load on. Yeah. Well, that's a bummer. Alright, y'all, so once you get to a point in a repair where, you know, if you're starting to have trouble, you eventually get to a point where you've got to sit down and learn more about the circuit. Otherwise, you're just going to keep guessing and wasting time, checking components you don't even need to check. So that's what we have to do here. Okay? We replaced these two power MOSFETs, and the supply is still not providing 12 volts. So, got to figure out a little bit about the circuit. Now, when I have a power supply like this, what I like to do, and I'm having issues, is take a look at the power management IC. Switch mode power supplies like this are going to have a power management IC, and they've come in a variety of different kinds. Some are a lot simpler, where they're literally just a pulse width modulator and MOSFET combined. They're known as AC-DC converters. Others are a bit more complex, where they might combine power factor correction and the AC-DC converter in one, or they might be separate. But you start with that guy because it's basically acting almost like the brain of the power supply. Okay, it is usually acting as the PWM, or it's controlling the switching of the MOSFETs. And so you can probe this guy with your oscilloscope, check out the waveforms, make sure it's getting power, and that can tell you a lot about what's going on with the unit. So that, for this supply, that is that 16-pin IC right here. Now, let me see if I can get this on camera. I guess I can't, it's not really coming up. But anyway, it says, yeah, there it is. DAP 053T, right? So, I couldn't find anything on this IC. And it looks like it is a Sony proprietary chip. And so you can't get any information on it. Now, there is so much information about this supply online regarding repairs, or just repairs in general on the PS5, and I don't want to look at these videos because I want to figure this out for myself. But I did briefly look at one video that pretty much states that there's a alternative to this that can be used, that's available for purchase to the public, and that is, let's see, this guy, this TEA 2016 AAT. So this is a, let's see, an LLC and PFC combo controller. Alright, so I think this is a good time to define those terms. Let's start with PFC. I mentioned that earlier. That's power factor correction. Alright, so when you're dealing with a power supply like this that's using a filter capacitor, which are these big caps here, or non-resistive loads that have capacitors and inductors, that causes problems for the electrical companies that supply power to us, because they change the power factor. When you're dealing with strictly resistive loads, that power factor equals 1. When you throw in capacitors and inductors into that, that power factor starts to drop below 1, and that causes problems for the power company, and it makes our grid less efficient. So this power factor correction has been developed to bring that PFC, that power factor, closer to 1. And so that is done. There's a number of ways to do that, but in this supply, and you can tell by the topology, that's being done by active power factor correction. So that's done by a switching MOSFET that is acting as a boost converter. Now, a boost converter is stepping up that voltage using a MOSFET, which is this guy right here, this one right here, and a diode, which, So the MOSFET is, well, there's more components than that. There's also an inductors that are involved. So the inductor, it's basically transferring energy from an inductor and into and pumping up charge into a storage capacitor. And so by increasing the charge of that capacitor, you're able to increase the output voltage. Okay, so and to do that, you need this switching MOSFET and this diode. So that's what these two are doing. Now, because this supply is available for use for a wide range of input voltage, I don't have the back panel, but I did show it earlier. It says it can be used for 120 volts and 240 volts. And most switch mode power supplies today, if you look at the back of a piece of equipment or electronic device, it'll usually say can be used from like 85 to 265 volts or something like that. So in order for power factor correction to be done for all those inputs, the boost converter needs to step up that voltage to roughly 400 volts. So that's why these capacitors are rated for 450 volts. So if we put if we measure the voltage across these capacitors, we should be getting roughly 400 volts. Otherwise, it's a good chance that this chip is not doing what it's supposed to do. So that's one thing. So that's PFC. Let's talk about LLC. So that is a form of switch mode power supply. And I've got some really good application notes that go into more detail about PFC and LLC, and I'll put that in the description. Basically, it is a type of switch mode power supply that is allowing for higher switching frequencies and reduced switching losses, so they're more efficient and are used for higher efficiency applications. Now, we're talking about a PS5 that requires a power supply that is able to output 350 watts. You're going to want a power supply that's really efficient. And so this is basically breaking it down into this block diagram where you have this half bridge here of two MOSFETs. So these are the power switches, taking a DC voltage and making it a square wave. You've got this resonant tank, which is a series of inductors, or it could be just one large inductor, making it into a pure sine wave, and then the transformer followed by your diode bridge, which then again helps to rectify it back to DC. The layout may not look exactly like this on the supply, but we can look at what's going on here. These two MOSFETs here that we replaced are part of that half bridge for the LLC. So it helps to get an idea of what these what's going on with the supply, get an understanding how the circuit works to allow you to repair it. Now, like I was saying, it's good to find that power management IC and look up the data sheet. So it's going to define all the pins on the IC. So here you go. So for example, the gate PFC, so that is the gate to that PFC MOSFET, so you can check that to make sure that there's a signal coming from there. Otherwise, that MOSFET isn't switching and the unit isn't going to be doing power factor correction. So that's one thing we can check. You've got this pin here, pin 13, so that's the supply voltage to the IC. Are we getting voltage to the IC? Otherwise, it's not going to work and none of the MOSFETs are going to be switching and we won't get any voltage. So that's something you can check. So we're going to start checking some of these and see if that leads us anywhere. Alright, so the first thing I wanted to do is check the voltage across one of those large filter caps. So like I said, if the PFC circuit is working, we should be seeing around 400 volts DC, close to. So let's check that. Now I'm checking it from the back side of the board. This is one of those caps. Okay. Well, that is good. It's still dropping down though. That's not right though. Yeah, I mean it shouldn't be. It should have. It should be staying at that voltage. It's almost like it got charged up to close to 400 volts, but it's now discharging slowly. Yeah, it's still going down. So that's not good. Alright, so right now I'm probing pin 5 on the power management IC, sorry. And watch the oscilloscope screen when I turn it on. Watch what happens. Did you see that? So that explains why those caps got charged and now they're discharging. Because that's the gate to the PFC MOSFET. It just stopped switching. So something's not right. That should keep switching. That's the gate to the MOSFET, which is the signal that's allowing the MOSFET to switch on and off, and now there's no signal. So something's not right there. Alright, so I'm going to do the same thing for the pin 13, which is the supply to the IC. You can see that the signal on the scope is slightly above ground. It's at roughly 1 volt now, but it's coming down, and that's because I didn't discharge the filter caps. So let's turn it on and see what happens. Okay, so the voltage, you saw it climbing up, and then it came back down, and now it's doing this weird thing. Okay, there's some ripple on there, but I mean that's what it looks like. But let's go to AC. AC coupled, so we can look at the. Yeah, see, that's not ripple. Yeah. Yeah, so if that was ripple from a bad capacitor, you'd be seeing, it wouldn't look like this. It would look similar, but the frequency is wrong. It would be at 120 hertz. That's something else. And I actually looked at this in the manual. That is hysteresis. And let's take a look at the manual, and I'll show you guys what I mean. Alright, so we're looking at the data sheet now for this TEA 2016 AAT. Now, keep in mind, this is not the data sheet for this IC that's on the board. Like I said, it's a proprietary IC from Sony. We don't know how different they are, how similar they are, but based on some of the things that it's doing, it seems like they're pretty similar. And so right now I kind of have this flow diagram for how the IC starts up. So you've got, no supply. So right now the IC is being supplied not by the auxiliary winding on the transformer, but it's being supplied by the high voltage at the power factor correction MOSFET, the drain of that MOSFET. And so it kind of goes through these startup settings, and you can see here the PFC is disabled, the LLC is disabled, so that's the gate or the signal to the gates of that half bridge, those two MOSFETs that we replaced. But you can see right about here when it goes through all those settings that the PFC is then enabled. And so we saw that the PFC was enabled, and then all of a sudden it stopped. So actually what I'd like to do next is check to see if the LLC also ever starts up, and maybe that might also provide a clue as well. But what I wanted to show you, that signal that we were looking at, so this is the hysteresis that we were seeing. This is the signal we were seeing. So it looks like that can occur for, you know, when the system enters some kind of protection mode. So there are a few different reasons why it could occur, but you know, it's not some sort of ripple from a bad capacitor or anything like that. So I think we need to do a few more measurements to figure out why this is happening. Alright, so now we're going to check the high side gate. See if the LLC comes on. Alright, yeah, same thing. Same thing. So the LLC is also starting up and then stopping. Alright, let's check the low side now. So that's pin 6. Whoa, what was that? That's interesting. That's really odd. I don't know. I was assuming that it would be the same exact signal, but that's interesting. Okay, back to the data sheet to see what's up with that. I don't know if that's supposed to do that or what. Wow, so I don't know if I found the problem, but this is certainly another problem. So this is that resistor that I had to resolder. That was just the joints were so dry that it was just, you could just move it around in there, and they were also burnt. And I think that's where that burn mark came. I could have sworn that I measured it and it was good. Now this is an 0.1 ohm resistor. Okay, I could have sworn I measured it and it was good, and it's clearly not. So I don't know if this happened in the process of powering it on or if I made a mistake, but this is definitely going to cause issues. So I mean, I think I have something close enough to pop in, and we'll definitely know for sure if it goes short again. But yeah, I'll see what I have. All right, there's the new one. Popped it in. Now that's a 2-watt rated resistor. It's probably the same. It's just a different shape, although I could be wrong. But that's the only thing I had that's close enough. Let's see what happens. Let's power this guy on and see if it blows up, or I don't know. Okay, so I figured we'd start with the same test, except we're going to be just checking the supply voltage to the power management IC. So that's pin 13. All right, I'm going to turn it on, see what happens. Oh, uh-oh. Oh man, it's not happy about something. I just heard something really odd happen, and now it's just doing that hysteresis again, it seems like. I think we might have killed another MOSFET, because from gate to source here, reading at 166. I don't know. Or something's not right. Alright, so now I don't know what's going on, because now if I check between gate and source, it's back up to 10K. And that's what the other one is. I swear, I removed the MOSFET. It's not the MOSFET. And even after I removed it, it was still measuring around 170 ohms. Alright, so I'm going to monitor the gate of that high side MOSFET. Yeah. And the same thing happened, the same sound, and I don't know what the hell is going on here now. Alright, so I'm trying to get a good view of this. Right now I've got two probes on the board. Probe number one, which is currently the one that's a bit lower, that is on the gate of the high side MOSFET. The other probe is on the drain of the high side MOSFET, which is also the HB pin, or I guess it's the half bridge pin, which is pin 11. Again, I tried powering up again. Same thing happened where the gate voltage went through the roof and it started doing this charging like at a very slow rate, like 4 hertz. So that's very slow. It almost looked like a capacitor that was being charged, then discharged. So yeah. And then it would recover. I would power it down, discharge the caps. There would be 4 ohms, or basically a short across pins 9 and 11, and then out of nowhere it would go back up to 10K, which is what it's supposed to be. So the only thing I can think of where that could be occurring is on this power management IC. Maybe something thermally is going on there where it's cooling back down. Something is causing a short between these pins for this to happen. Alright, let's try powering this on again and see what happens. Wow. Yeah, almost immediately they both... Yeah. There's got to be something wrong with this IC. It is Christmas time in the lab. So the components that we need came in. Now we don't need all of these components, but usually when I place an order for 1 or 2 components from Mouser or DigiKey, I'll throw in a couple others that, especially if there's others on the board that I'm working on that are common, that could potentially show up on other boards, and you know, they aren't too expensive, I'll place an order for them if I don't already have them. So that's what all this other stuff is. But this is the dual N channel MOSFET for the motherboard, and this is the power management IC, that TEA 2016 AAT, that will replace the DAP 053 T. I think I'm getting that right, but yeah, so that's that power management IC. So we got what we need to continue this repair. All right, we got our new power management IC soldered in. I like to use, when I'm dealing with an IC like this, I prefer to use Chip Quick. It's just easier to, in my opinion. You don't have to worry about knocking off any of these other smaller SMD components with your hot air. It's easy to clean up too if you're once you get the hang of it. So that's what I use to I should specify, because Chip Quick makes a lot of different things, but this Chip Quick removal alloy, it's just got a lower melting point than your normal solder, and it mixes in with the solder, brings the whole melting point of that molten mixture down so that you can remove the chip a lot easier. So that's what I used. Got the new one in. It's looking good. Let's power this guy up, see what happens. Well guys, it is working. Check that out. I mean, it's working. And the wave, what's kind of confusing me is the you know, the high and low side MOSFET gates are completely different. So I don't know if it's just in some sort of weird low power state, where I'd be curious to see if the waveforms would change, putting a load on it, which we can attempt to do now with the electronic load here, but it's working. Check that out. That's awesome. Alright, you can see we've got the unit hooked up to the electronic load. It's no load on it currently. It's outputting about 1 watt. If I can safely probe one of the MOSFETs without this killing this thing. Okay. I forget if that's the low or the high side, but this is the waveform we're getting. We're going to start with 50 watts. I hope I don't kill this thing. But if this does kill it, well, then it's going to be no good for the PS5. But yeah, let's just turn on the load. Okay. Okay. Oh. Whoa. Yeah. So I should be really doing this with a high voltage differential probe, because you can see here we're clearly, you know, maxing out the display, because this is roughly peak to peak 400 volts. So I think that would be a better idea, is switch out the probe for my high voltage differential probe. Let's do that. Alright, so we got the high voltage differential probe out, so now it's a you know, it has an attenuation factor of 100, so we can really see those higher voltages. And we're probing again one of the LLC MOSFETs, and so now it's got no load applied, and you can see that this, I was looking at the data sheet for this chip. There's also a really in-depth application note for it as well, which goes into even more detail on how the thing works. And my camera unfortunately is doing some really weird, well, let's see if we can trigger on this a little better. Yeah. Well, anyway. This is actually how it looks in burst mode, which is when, for low loads, and in this case here, zero load, it's a way for the power supply to maintain efficiency at lower loads. And it's very similar to what the application note is showing. And then you've got this up here. You can see these peaks here. And if we zoom in a bit, you can actually see them right there. How cool is that? That's very neat. Like that's really cool. And so now we can check how this waveform changes by increasing the load. So we can turn on our electronic load, put on that 50 watts, and now you can see that frequency, the amount of peaks has increased. There's no more holds or pauses in between. Right? See that? It's very cool. Very cool. And we can even take this up a little bit. Let's see. Let's increase this load a bit. Let's do 100 watts. Please don't die. Oh. Uh-oh. It made a funky sound. Oh, I don't like that. I do not like that sound. Let's turn this guy off. The hell? Yeah, that's not good. I don't know why it's making that sound. That's really strange. It definitely sounds like it's coming from the resonator tank or this big inductor. Like, what is that? That's so odd and scary. Very scary. Yeah. Alright, so now I've got my passive probe hooked up to the output of the supply. I just wanted to check the ripple on the output, or PARD. And so here you can see we've got 12 volts. It does look clean when we're DC coupled, but let's AC couple that. So it does seem like there's a bit of noise. But yeah, I don't know if that's due to if that's just intrinsic of the supply, or if those are caps that are starting to go bad. But you know, peak to peak of roughly 20 millivolts. I'd be curious to see how it looks with a load. Alright, I pushed it up to 120 watts, and it's just, you really need to do this measurement right at the supply, and you know, so it's just going to add too much noise. And actually what I'm doing right now is adding averaging, so it's going to bring all those random peaks down. It's gonna smooth out the signal, so you know but I'm not really seeing any ripple from that you would see more typical ripple. But man, that noise from that resonator is just horrendous. So I don't know, this thing's supposed to be capable of 350 watts. How loud is that gonna be at we're not even halfway there. So I don't know. Yeah, so this application note does mention that noise that can be caused from the resonator. The main mechanism for producing noise is the interruption of magnetization current sequences, leading to a mechanical force. The core of the resonant transformer is especially susceptible, starts acting like a loudspeaker. And it seems that if the duty cycle is increased, that noise should go away because the switching frequency starts getting out of the audible range. Now, it probably already is out of the audible range, but due to harmonics and this burst mode that comes on and off, we can hear it. So it's just so loud that, and it seems to get worse with as we increase the power, the load. So all right, I got it up to 150 now. I'm about to put it up to 200. The noise is not stopping, so let's see. Yeah, it's definitely gotten louder. Yeah. Alright, that's enough of that. Yeah, I don't know. But, I mean, it's still putting out a clean output. Alright. 250 watts. And, man, that thing is chirping away there. Excuse me. Does not sound good. But, I mean... there you have it. Yeah, I don't know if that's again the replacing it with the TEA 2016, because that sound is due to it switching from burst mode to in between bursts. At least that's what the datasheet says, or the application note says. But yeah, and I don't know what. It's a 350 watt supply. We're at almost 24 amps right now. It can do a max of 31 amps, so we're pushing it. Yeah. Well, I know I said I was going to do the motherboard, but I think I'll have to save that for another video. But despite the noises, I'm going to recall this a success. You know, if you've repaired one of these or come across one of these and have any other input on the noises that this thing is making, let me know if there's something I'm missing. But yeah. Yeah, like I said, I'll have to do the motherboard in another video. The short on that board definitely due to that MOSFET, so we'll replace that, see where that gets us, and kind of go from there. I hope you guys found this interesting. I know that there are a ton of videos online repairing these, whether it be the power supply or the motherboard, but figured this might be interesting still, and also to give you guys a little bit more information on PFC and LLC converters or switch mode power supplies. I'm sorry. And yeah, I mean, I did check on a few more videos after I fixed this, and I'm pretty impressed by the amount of people who just repair these without an oscilloscope, or, you know, maybe it's because there's so much information out there for these, but yeah. But anyway, guys, have any feedback, as always, leave it in the comments, and I'll catch you at the next repair. Alright.